Good afternoon, everyone. My name is Katrina Croft-Cusworth. I'm the Communications and Events Coordinator for the Melbourne Energy Institute. Thank you all for joining us today for the fourth instalment of our MEInetwork Seminar Series with a focus on gas supply chains and alternatives. Before we begin, I'd like to acknowledge that today we're gathered on the lands of the Wurundjeri, Woiwurrung and Boonwurrung people, who have been custodians of this land for thousands of years, and we acknowledge and pay respects to their elders past and present. Today we're joined by three speakers: Mr. David Norman, CEO of Future Fuels CRC, Mr. Steve Davies, CEO of the Australian Pipelines and Gas Association, and Mr. Robert Davis, Senior Engineer for Low Carbon Futures at the Australian Gas Infrastructure Group. Professor Pierluigi Mancarella, MEI's Program Leader for Energy Systems, will moderate today's discussion. So thank you to our speakers for sharing their expertise with us today. And over to you, David. Thank you.
Thanks very much, and a warm welcome to everyone here in the room at Melbourne and also online. I'll just get this operating. There we go. Okay. My name's David Norman and I'm the CEO of Future Fuels Cooperative Research Centre, or CRC. And today, during this seminar, we've been asked, or we're very pleased to have been invited by MEI to give a bit of an overview of the existing infrastructure for both transmission and distribution of gas in Australia, as well as extend into a bit of a deep dive on the opportunities that both these parts of the network have for energy users of the future, and a little bit more detail on some applied research, international experience, and some of the new knowledge that's occurring as part of this transition to net zero. I'm very appreciative of some industry experts in this area that have joined me today, particularly as we've had a number of people fall sick in the last couple of days. So both Steve and Robert have had to join at the very last minute. But after I do a few scene setting comments, we're going to hand over to Steve to talk in more detail about the transmission system. And then Robert and Steve comes from the association that represents what's often called the pipeliners, or the transmission element there. And then Robert from AGIG, one of the distribution companies, who will talk in more detail about distribution. Then I'll come back and give a little bit of an overview of both some of the research work we're doing here, our interlinks with overseas, where there's so much activity going, and some of the programs and other initiatives occurring in this area. So in terms of setting the scene, I think it's very important to provide a little bit of context about which part of the gas value chain we're talking about here. And we've deliberately put the red circle, red square, around the gas transmission and gas distribution, which is not the production of gas as it occurs conventionally at the moment, or the production of clean gases, such as hydrogen and biomethane in the future, as well as in the downstream side, when you get beyond the distribution, the whole issue of energy retailing, and then the customer piece, whether it be residential, small industrial or commercial. And I think key inside that red box there is that the gas transmission is the high pressure, often large pipes that are almost like the interstate highway for moving gas long distances through high strength, high pressure steel pipelines. And in Australia, we've got nearly 40,000 kilometres of those moving gas very long distances. That then arrives at a city gate where the pressures are stepped down and then run through a much larger system that you'll hear about later, called the gas distribution, which steps pressures down through a high, medium and low pressure system all the way through to end customers. In the gas transmission system, I think it's very important that off that high pressure, very large industrial customers often come directly off those links, as well as interlinks with gas storage, and particularly underground gas storage, which is a key component of the opportunity of the future as well in hydrogen, where the very economical, very large scale storage can be interlinked through that system, as well as interlinks with power stations and the role that particularly hydrogen can and will play in firming the power system or electrical system, as well as the interlinkages through export as well. And finally, in terms of just setting a little bit of context, There's many different ways to look at this, and there'll be some more details later on in some of the other presentations, but I thought it was sort of important to give a sort of context to the amount of energy as it stands today, realising that almost all of this gas today is, of course, methane, a fossil fuel that we have to, as part of net zero, move out of the system. But the ability of this infrastructure to be adapted and repurposed, as well as new, to actually carry net zero fuels such as hydrogen. But as they stand today, the gas that's used, almost 1,200 petajoules, a measure of the energy there, about 14 or 15% is used in residential, which is a smaller component, but is important in terms of the peakiness of that demand when it comes to pathways forward. About 37% in electrical generation, and about half of it used in commercial and industrial, manufacturing, mining, etc. And in CO2 terms, this equates for about 12% of Australia's current emissions. Therefore, crucially important that we actually are working through each of these pieces on a net zero story. And when we look forward, there's other elements in future gas system actually might and will come forward. The issue of transportation is not really covered by the current gas system, but in future transportation, we see two main pathways. One is the full electrification by battery electric, and one is the electrification by fuel cells, electric vehicles running on things like hydrogen. I just note here in terms of the scale there, that it's about 1.5, a bit more times the current energy supplied through the NEM electrical system. And I think that shows a measure, and you'll see later on that of the total energy demand, currently electricity is about 20%. Electricity under every scenario is going to grow dramatically, but it's the role of some of these other elements, like clean fuels, like hydrogen, that is key to how and where parts of the existing networks will be utilised. And I do quickly note before we go on, there's a lot of terms here. We've used hydrogen, but hydrogen is one of what we would call the renewable gases or clean molecules. I think it's important to recognise other elements too, because they do play into future network design, such as biomethane. There's others, if we want to get more complicated, synthetic methane and syngas and some of the derivatives as well, methanol, ammonia, etc. And key as we look forward is the role that hydrogen can and will play in what I would call the hard to decarbonise sectors, such as heavy industry, inevitably a big role for hydrogen. Some where there's no alternatives, somewhere hydrogen will be both economic and an easier, although never easy in this complex transition, an easier transition pathway. Then there's heavy duty transport I've already mentioned, the issue of decarbonising the whole heating system, let alone the other elements of firming the power system, large scale storage, and also of course, critically important for Australia, the export of clean fuels such as hydrogen. I'm now going to pass on to Steve Davies to talk about the transmission system. Thanks, Steve.
Thank you very much, David, and thank you very much for the opportunity to talk to you all today about Australia's transmission pipeline infrastructure. So when we're thinking about gas transmission infrastructure, we're talking about high pressure steel pipelines that transport gas long distances, typically from where gas is produced to where it's in demand, industrial centres, capital cities in Australia. As the network has grown, the East Coast gas grid in particular, we see gas being transported from pipeline to pipeline as well around the country. High pressure, what does that mean? Technically, a high pressure pipeline is one that operates between 1 megapascal and 15 megapascals. Atmospheric pressure is 101.3 kilopascals. So somewhere between 10 and 150 times atmospheric pressure. In Australia, our long distance pipelines tend to be at least 5 megapascals. So that's 50 times atmospheric pressure. And if you cast your mind back to high school or university chemistry, the ideal gas equation, PV equals nRT. As you increase pressure, you decrease volume. So if we're operating at 50 times atmospheric pressure, that's a very large amount of gas we can start putting into these steel pipelines. And they move a lot of energy. You know, you're just looking at the the two maps there, you can see our electricity transmission infrastructure tends to hug the coastlines, and the colours you can see are overlapping as different transmission lines serve similar regions. Whereas on our gas transmission infrastructure, there are a couple of major pipelines feeding into most capital cities. So capital cities tend to be serviced by one or two transmission pipelines, and the gas demand in any given city varies around the country. But here in Victoria, there is more gas demand than electricity demand in Melbourne. So not too many pieces of infrastructure required to get the necessary amount of energy to any given space. If you look at our map too on the gas transmission side, you can see that pipelines extend over most of the country, and that's a sign of how good they are at transporting energy long distances and how economic it can be to do that. To put it in context, on the east coast of Australia, not including our connection into the Northern Territory there, we use around 600 petajoules of gas, which is, as David said, it's around the same amount of energy as the NEM. And that's moved by those pipelines you can see in Eastern Australia. That is a lot of gas and a lot of energy for the Australian context. Compared to what infrastructure in the Northern Hemisphere does, it's not actually that much. So the one I like to visualise on this is Australia's entire East Coast gas demand is about the same as Belgium's gas demand. And Belgium is half the size of Tasmania. And we can see how big the East Coast is there. So our infrastructure does a job that no one else's infrastructure in the world does. It transports relatively small amounts of gas, very long distances. Some of those pipelines there are over 1,000 kilometres. So Australians are actually world class at building a certain type of pipeline, which in the industry we call long and skinny pipes. They're not particularly wide. The wider you make them, the more gas you can fit in, and the longer. So there's no other country or region in the world that is building pipelines as narrow as ours and as long. You'll see narrow pipelines over much shorter distances. You'll see longer pipelines that are much wider, transporting huge amounts of energy across Eurasia. But what we do, not even just better than anyone, no one else even does it like we do in terms of those long, skinny pipelines. So that's transporting a lot of energy. That said, a single pipeline can transport a lot of energy too. So on this map, you can't really see it. There are 3 pipelines from the Queensland gas fields in the Surat-Bowen Basin going into Gladstone for our East Coast LNG export industry. Each one of those 3 pipelines transport roughly the same as the entire East Coast gas demand. So you can have one pipeline transporting as much gas demand as the entire East Coast, or you can have a network of roughly 20,000 kilometres of pipeline transporting that same amount of energy throughout the country. And the fact that we can do it in a way that is still affordable for us for gas to be highly competitive is testimony to the characteristics of gas infrastructure. Because that compressibility, that pressure that I talked about earlier provides us great opportunity to move high volumes of energy consistently, but also store a lot of energy. So the longer we make our pipelines, the more energy that is actually in them. And gas does not move super quickly. Let's say Moomba to Sydney is a good example. Gas goes in at Moomba on a Sunday. It's getting to Sydney by Wednesday, so about 3 days worth. You could stop putting gas in at Moomba and gas would still be delivered to Sydney for the next 3 days. If you think about maybe a balloon that you blow up and let go, air comes out for quite some time. So that is a huge amount of energy storage, which currently is not something we've been too focused on. Certainly gas customers think about that reliability and that ability to maybe stock up on gas before particularly cold days. But as we go through the energy transition and energy storage becomes even more valuable, this is another opportunity for that our pipeline industry presents to store energy as we transport it as well. And you'll often see a gas power station has a big spaghetti line of pipeline going into it so that it has the energy that it requires whenever it wants. Before I move on to the next slide, I guess the one thing I like on this map for the gas transmission infrastructure to illustrate that capability of gas and the economics of gas infrastructure. You know, Mount Isa's up there close to the Northern Territory, Queensland border. It's a huge industrial centre in central northern Australia. It's connected to the East Coast gas grid. It has gas power stations generating electricity there. It's not connected to the electricity grid. So, you know, the numbers have been done. It makes a lot of sense to transport and store gas and generate electricity on site. You won't find any gas power stations anywhere in the country that choose to locate close to gas and transport electricity long distances. They all choose to transport gas long distances and generate electricity close to electricity demand, just to give an indication of the relative economics of doing both. Thinking more about those economics and the cost effectiveness of gas infrastructure, I've got some numbers there looking at transmission and distribution infrastructure here in Victoria. Victoria is a great example because it does have such a high gas demand due to its weather, where we need a lot of heating in winter. So in terms of actual delivered energy, gas is delivering about 50% more energy than electricity in Victoria. So 65,000 gigawatt hours to 42,000 gigawatt hours. But the regulated asset base, so this is approved by the Australian Energy Regulator, the cost of the infrastructure is $5.5 billion compared to $17 billion for electricity infrastructure. So 1/3 the asset value. The actual annual revenues, which is a good reflection of operating costs, but it's also reflecting a return on those asset values, is 1/4 for gas infrastructure what it is for electricity infrastructure. So it's delivering more energy, 50% more energy at 75% the annual operating cost. Sorry, 75% less, 25% the annual operating cost. And also importantly, that maximum demand capacity. So in winter, when it's cold and we need a lot of energy, gas is delivering, 23,000 megawatts of energy at any given moment at its peak demand at times. And that is much higher than what electricity is capable. The electricity system in Victoria is capable of delivering at its peak demand time in summer at only sort of just under 9,000 megawatts. Reliability, something I haven't touched on, is all of Australia's gas infrastructure is buried. That's done for safety reasons. You know, when we are talking about transporting these amounts of energy in what is ultimately a quite flammable gas, and we like it because it's flammable and that gives us the ability to use that energy when we want to. Burying it makes it much easier to protect. We don't have to worry about vehicles crashing into it, or that's really the biggest one, but there's all sorts of things that can go wrong with above ground infrastructure. Weather events, bushfires have caused issues for above ground infrastructure across Australia. So, pipelines experience much lower impacts to supply than our counterparts in the electricity industry do. And you'd all be familiar with the saying, in the pipeline. That means something is on the way. Not it might happen or it's going to happen one day. When we talk about an investment pipeline or project pipeline, these are things that are in process and will happen. And that's because of the reliability of pipelines, is where that original saying comes from, or the origin of that saying. We're really interested in what gas infrastructure can do to assist with the energy transition. David mentioned that electricity is currently 20% of Australia's energy supply. I mean, this is looking at final energy consumption, which is quite different to primary energy consumption. This is the energy actually used by the Australian economy. So gas is currently providing 24% of our final energy consumption, in addition to providing the fuel for 20% of our electricity generation as well. And liquid fuels actually supply more than gas and electricity combined. So this leads us to think there's a huge opportunity here for the gas industry to assist with decarbonisation, because there's an awful lot of work going on in the electricity space to 2030. That's focused on decarbonising the current electricity supply. We're interested in getting on with decarbonising the gas supply as we move forward. And these are the questions that we're asking ourselves: is maybe not can we help, it's how can we help? How can we show the potential of gas infrastructure. And I'm going to move into a few slides coming up talking about that. One of the things I want to be very clear that we don't know, like our existing infrastructure at the high pressure steel end, it's different for distribution, which Rob will be talking about, is designed for natural gas, and at high pressures, there will be challenges getting a lot of hydrogen into that infrastructure. So I can't tell you how much hydrogen any given pipeline can transport. I can't tell you how much it'll cost to modify an existing natural gas high pressure steel pipeline to transport hydrogen. But I can tell you how much it'll cost to build a new one. We can build a new hydrogen pipeline, high pressure, long distance today. We'd use different types of steel, different types of coatings to what we currently do, and that's highly doable. And all we need to know as we move forward is, will the cost of modifying an existing natural gas pipeline be less than the cost of new build? So what we've done as an initial study for the pipeline industry in Australia, and to inform the conversation, is we had a look at the options to transport energy going forward from both pipelines and power lines. Looking at multiple transmission distances, from short distances of 25 kilometres through to long distances of 500 kilometres, throughput capacities for quite small, which what we see at the start of the hydrogen industry, through to 500 terajoules a day, which is sort of approaching half the entire East Coast gas demand now. The storage scenarios of 4 hours, 12 hours and 24 hours, looking at hydrogen pipelines, natural gas pipelines, high voltage AC and DC, all new build, comparing like for like. What we found, and you can find all of this if you Google pipelines versus power lines, the report's available online. We're happy to talk about any of the assumptions that went into it, any of the findings. The reason I talked a little bit about what's going on in Mount Isa in that first slide is because that's a real world example where the decision was already made to transport gas over electricity. The levelised cost of transport across all those options, much cheaper for pipelines than it is for power lines, due to the compressibility of gas. It's got physical properties that we can take advantage of. And you can see whether it's a short distance or a long distance, just on transport alone, pipeline infrastructure is going to have major cost advantages over electricity infrastructure. And on storage, it's an even more pronounced advantage, because even without designing for storage, pipelines already have that storage component. And then if you want to start sizing the pipeline beyond what you need for your daily demand, you get large amounts of extra storage at very low prices. So when we're thinking about a green hydrogen economy that is reliant on cheap and excessive solar being around the place, if we go from solar to hydrogen and transport hydrogen in pipeline, we're instantly getting, at the end of the pipeline, energy that's available 24/7. Whereas if we're sticking with solar and transporting electricity, we've got an electricity storage issue that we need to deal with as well. So there's a lot of opportunity there. There's also a lot that needs to be done in this space, and David will talk about the research that is going on. But we certainly see that our high pressure steel infrastructure has a lot to offer. It already is in terms of what it delivers at the cost it does, but what it can do in the future as well. And from there, I might hand over to Rob, who'll talk about the capability of our distribution networks.
Thank you, Steve. And g'day, everyone. Thank you very much for having me. As Steve mentioned, I'll be chatting about distribution networks. I'm an engineer, so I've got a few graphs, a few pictures. I'm going to start off with a bit about who AGIG is, a bit about how the distribution network looks and feels and operates, a bit about energy consumption specific to Victoria. Then I'm going to go a bit about AGIG's vision for the future and some projects we're doing at the moment. So let's get started, shall we? So AGIG, Australian Gas Infrastructure Group, owns gas transmission, gas distribution and gas storage across all of mainland Australia. One big pipeline over in the west, which supplies most of WA's gas, or a fair chunk of it. Then gas distribution in terms of supplying all of Adelaide's consumer domestic market, 2/3 of Victoria's domestic market, and half of Queensland's domestic gas market. We're engaged with all the regulators across Australia, and that's a big part of as of looking forwards, Future Fuels, Future Energy for AGIG is dealing with those sorts of regulators. In terms of what a gas distribution network looks like, touching and feeling it, because this is a question I get asked a lot and people generally don't have a great understanding. Steve talked about transmission pipelines at the top. You can see long distance in the middle of nowhere, big diameter steel generally. Where I've spent most of my working career is in the distribution, where we take through pressure regulating facilities, the city gates that Steve mentioned. We take that, we depressurize into the generally plastic networks you'll find within the cities around Melbourne, where we transport it through a very grid-like network to our customers, and pretty much everyone's got in Victoria at least has a gas meter at the front of their house, like that. So I'll be talking about those bottom three rungs today. Rungs, pictures, sweet. This is a map of Albert Park Lake, and I wanted to show this map, or what the gas distribution looks like in practice. This one actually has a transmission pipeline running through it. So we do have transmission pipelines running through the middle of city centres, just much lower pressures than the ones Steve talked about. But you can see every blue, green and black line is a gas pipeline. It pretty much runs down every street and is highly interconnected. And Steve talked about reliability of pipelines. Reliability of the gas distribution network is because of that interconnectedness. If you have an issue in one area, there is multiple feeds to every customer. In general, most gas networks across Australia are in the process of upgrading their entire networks to high pressure. Those low pressure networks were built up to 100 years ago and are nearing the end of their life. So in the process of replacing everything with high pressure pipelines, which will give some of that extra storage. All polyethylene. All right. So in terms of gas usage, this is specific to Victoria, and there's a couple of points, or 3 points actually, I wanted to share with this one. First of all, a description. You've got how much energy the electricity network provides in Victoria in the dark blue, how much energy the gas distribution provides in the light blue. Then you've got the transport sector, excluding aviation. And then the black line at the top is the sum of everything. Down the bottom in yellow is how much large-scale renewable we've got. So the first point is, as a society, our goal is to get that yellow line up here, which is a huge challenge. The second point is, as Steve mentioned, about the amount of gas is used in Victoria. You can see, A, it sits higher than electricity, but B, it is much more peakier, given that residential heating load through winter. And that is that for that slide. So that, in terms of that sort of sets the scene, we've talked about AGIG, what a gas distribution network looks like, where the challenge is. So what's the vision? Where does AGIG see the future? Our low carbon vision, and this is echoed through the Gas Vision 2050 part of the as a gas industry. But by 2030, we're looking at greater than 10% renewable gas in our distribution networks. And as was mentioned earlier, renewable gas, hydrogen, biomethane, and others. 2040, 100% renewable gas in our mains. So that's the vision. What are we actually doing about it as a company? This is a list of all the projects that are currently up and running or are planned in the near future, and is just the first snapshot, and I'll go into depth about our longer term vision. You can see we've got projects going in every state, and this is deliberate to engage with every regulator and get everything on track. You might have heard of Hydrogen Park South Australia. That's up and running, delivering 5% blended gas to customers, about 700 customers in South Australia. It's been operating for 12 months. I'll get more detail in a sec. Hydrogen Park Murray Valley is the next one we're looking at, which is 40,000 customers in Albury-Wodonga, including industrial. We've got Hydrogen Park in Gladstone, which will do something similar in Gladstone. And Wagga Wagga just got shortlisted for funding there as well. Also biomethane project in South Australia with Edinburgh Park, injecting biomethane, and we've done a feasibility study on the DBP to see how that could transport hydrogen. That's just the ones that are either started or are coming in the very near future. I talked about Hydrogen Park South Australia. It's blending gas to residential users and has been for over 12 months now, and without issue. It's working great, and so well we're in the process now of expanding it to an additional 3,000 customers. We've also, as of yesterday, started selling green hydrogen to the steelworks, and that's replacing their former use of grey hydrogen from Victoria. So when I talk about a hydrogen park, it's not just for the gas distribution network, there's many uses, and the potential future is also vehicle refueling for these sites. Hype Murray Valley is sort of our big final demonstration plant before we switch to BAU and roll this out everywhere. It will be a 10 megawatt electrolyser at Albury-Wodonga on the Victorian New South Wales border. 40,000 customers, including heavy industry. So you've got everything. You've got brickworks up there, you've got forges up there, and you've got 38,000 residential customers using every appliance. So this will be the final demonstration project to show that it works. That'll be 10% blend. First production by 2024. And that concept includes a hydrogen hub as well. And oxygen, because waste oxygen is a very useful, or waste oxygen from my point of view is a very useful product. That's Albury-Wodonga. What do we have next? So where did these projects come from? Like they weren't just thought up and done. There is actually method to our rollout, and that method was developed through the Australian Hydrogen Centre, which was an ARENA-funded project. It's been running over the last 2 years or so, 2-3 years. That was my former employer. And that had 3 sort of outcomes, so to speak. First project was to look at which regional towns would be best set to do some demonstration projects and set up a sort of a checklist of which towns would be most suitable for doing blending. And that eventually became our Albury-Wodonga project as one of them. The second part was statewide studies for Victoria and South Australia, which mapped out a full end-to-end economic, technical feasibility and process of how we could convert, first of all, our distribution networks to 10% hydrogen and then 100% hydrogen. Being ARENA-funded projects, these will be published and they're due out in the next couple of months. So it's a very interesting reading if you want to see how a potential pathway to that could look like. The third one was to publicly release all of the learnings we had from Hype SA over the first 12 months of operation. That's coming out in a month or so. And I get the spoiler alert, nothing went wrong. So it's actually quite a boring report, but still an interesting read if you want to know how that. Now, the Australian Hydrogen Centre, I mentioned it was ARENA funded, but that was essentially Australian Gas Infrastructure Group and AusNet as the main distributors in South Australia and Victoria, along with NEO and NG as energy producers and retailers, and the Victorian and South Australian state governments were all heavily involved. Now, my last couple of slides is about compatibility of the existing gas distribution networks. And this is a very common question I get about how compatible are your networks? Like, can we put hydrogen in? Could they leak? Like, what will happen? And this was a huge focus of the AHC and part of what I was involved in. So I'll go through component compatibility, like valves, regs, meters, distribution piping, network capacity, and a few operational things. So for components, valves, regs, meters that we use to reduce pressure, stop flow, etc. In general, they're compatible, most of them, which is really good news. The size of the replacement program to make them hydrogen compatible is pretty small, and it's in line with our normal replacement programs that we do every year when components get too old anyway. Electrical equipment that we have installed in some areas does need to be upgraded to a higher level of electrical equipment for hazardous area reasons. And probably the big change you'll see as a consumer is the gas meter at your house, because they work on volumetric displacement. They'll be fine at 10% hydrogen because the extra volume of gas isn't that huge, but at 100%, they need to be switched out for a higher capacity meter, which again, seems like an issue, but not really, because we replace them every 15 years anyway. So we can replace them now or in the near future with something that will work on both and we will be fine. Distribution piping, so the plastic and distribution networks are predominantly plastic, but they do have steel and some other materials in them. That's generally fine for 10% and 100% again. And all joint types generally will be fine, with some further research being done at the moment on some fairly unique joints that are used not too frequently. Low pressure mains that I mentioned, the stuff in black that's still fairly common around the Melbourne CBD, that's been replaced currently as part of our mains renewal program because it's end of life. You could put hydrogen in if you wanted to, but we're probably not going to, and the mains renewal program will be finished before we wanted to put hydrogen in anyway. So that will sort that out. Network capacity is another one. So everyone knows that hydrogen is about 1/3 of the volumetric energy density of natural gas. So you need 3 times the volume to meet the same energy demand. And that does raise a few concerns about how much energy can we get through our existing network. But the good thing is that hydrogen has it flows much better through the pipes. We can flow it much faster. So once you actually, we run full models of our networks that we keep updated constantly. Once we switch natural gas with hydrogen in our models, the actual reduction in capacity is pretty negligible. At 10%, you talked about a 3% reduction in capacity, which is every network can take that, no worries. For 100% conversion, we lose around the 15 to 17% reduction in capacity, which again, most of our networks, because we just put in standard diameter pipes, most of our network is plenty oversized for that. Some parts may need a bit of upgrading, but they'll be very small. And then when it comes to operational processes, people's safety working around gas, what do we need to change? Well, for our hydrogen park South Australia and that area where we're doing 5%, we haven't changed any of our operational processes. It's all worked fine. For 100%, for example, when we're purging, greater control of emission sources when we're purging, hazardous area sizes change a bit, so exclusion zones around infrastructure might change a bit. And there's more research happening now about how we live weld into our steel distribution lines. So that in a nutshell, network compatibility, it's basically ready. So that's it for distribution networks. We've got questions at the end. So I hope there's plenty of questions. I love talking about this. But I'll hand back to David now to talk about future fuels. Thank you, everyone.
Thanks, Robert. I'm now going to just switch to a little bit about the research work that is going on in Australia, and then also expand a little bit to what we're seeing overseas, both with partnerships and exchange that we have, but also some of the other programs that are of direct relevance here. This is actually moving very, very fast, as the whole energy transition is. It's so pleasing to be in an environment after many years where we're not debating the end goal anymore. In fact, we're bringing such diversity of thought to achieving net zero. We're in a world now of what can we do and do relatively fast to actually achieve so much of this. The Future Fuels CRC was actually born, I think, before there was much talk about hydrogen, actually. A concept back in 2016, 2017 that was successful in the round of funding in early 2018, and therefore was about 4 years into a 7-year long-term partnership, which brings together over 100 different industry entities, 6 partner universities, including University of Adelaide, University of Melbourne, RMIT and Deakin, Wollongong, University of Wollongong, and also University of Queensland, and also a number of different state government entities. They're all in this fabulous framework, if I can call it, of the CRC program that's now been occurring for over 30 years to tackle big issues and bring diversity and aggregation together. It's very much an action-orientated applied research partnership where it's actually seeking out knowledge and answering industry-led questions throughout all of this area under 3 research programs, which are now delivering over 100 different projects. And involves a very large number of PhD and master students, but those 3 projects, or those 3 programs sit under 3 core areas. One's looking at the future of energy, future technologies, systems, markets, economic modelling, to try and understand where the drives are, where the issues are. Also does a bit of work on end user aspects there that we haven't gone into today. The second area is really very heavily around sociology, social acceptance, public safety, security of supply questions, and policy and regulatory. And then the third area is the hardcore engineering, what we call network lifecycle management. And described in this next slide actually highlights that we've got 10 working groups under those areas that look at things like the modelling, look at things like social acceptance, and in the network life cycle, particularly a specialty in metal assets, as you heard before, related to transmission pipelines, and plastic assets, as you heard, or polymer assets, as you heard, for the distribution. There's other topics there to do with integrity management and operations that are particularly important. So you can see a wide diversity of activity there. We'll go into 2 or 3 of those in just a little bit more detail in a moment. But in 2018 and beyond that, clearly we had a context of the gas industry, back in, I think, 2017, publishing what they called Gas Vision 2050, which actually talked about the role and possibility or the potential of repurposing and the new assets associated with moving and storing large quantities of clean gases. Now, if you have a look at current fuel systems, whether they be oil, gas, or even coal, the one industry that's got this potential to progressively decarbonise all the way through to a net zero fuel is the gas industry. And it's one where it started with that vision, and you can see in a few short years, it's put a lot of work and effort and investment and time in. The CRC is one example, but you also saw going from ideas of blending plants, of power to hydrogen facilities that take renewable electricity, solar and wind, and convert it through electrolysis to producing hydrogen, the activity that already has occurred on that first step, that blending step, which is a first step. Equally, during this time, the Australian government's National Hydrogen Strategy, chaired by previous Chief Scientist Alan Finkel, which we were involved in, particularly on one element, in particular of work of hydrogen in gas distribution networks, obviously. When we talk about converting and the new assets associated with hydrogen, it often feels like we're talking about a complete new industry. But in a sense, I think it's very important to sort of highlight that at an industrial scale, for over 100 years, there's been a very heavy component of hydrogen used, whether it's in the petrochemical industry or the ammonia. It's already a process and it's already storage that's been very heavily done. And I often highlight too that the town gas conversion of the 1960s shows that for the first 100 years or so of the gas industry in locations like Europe and Australia, we ran systems all the way through to homes that were a very significant portion hydrogen, up to 50 or 60%. And even today, there are some networks, such as in Hong Kong and Singapore, that continue to run that level of blend rather than having converted like we did here in Australia once before. Equally, in terms of pipelines moving not natural gas, but hydrogen, we've already got lots of examples around the world where long distance, high pressure hydrogen pipe systems are already operating. In the US, particularly in the Gulf Coast between Texas and Louisiana, there's well over 1,000 miles of high pressure hydrogen pipeline systems, and equally there are an equivalent system in Europe. In both locations, that has also involved converting existing pipelines across from gas or methane already to hydrogen. So we've already got a precedent of doing that. And a project which I'll mention in a moment, which I think is very informative here. The Europeans have developed an initiative called the European Hydrogen Backbone, which actually over some 40,000 kilometres of pipe looks at linking all the industrial areas of Europe with a high pressure 100% hydrogen system. And I think what's really informative there is that their initial work is assuming that 70% of that system will be repurposed pipelines. The other 30% newly installed, largely for reasons of capacity. I said I'd talk about 2 or 3 areas. I think one of the areas, and this is one area that we do work with Pierluigi and University of Melbourne's team on, as well as a number of our other universities, is the techno-economics of clean molecules and clean electrons interacting in the future, the integrated systems thinking that I think we're only at the infancy in energy planning of actually realising the importance of. And we have done work as a community on a future integrated gas, i.e. hydrogen and electricity model, which actually shows the incredible complementary behaviour between those two when we look into the future. The ability for electrolyzers to actually give us capability of managing stably a system when inevitably we're going from excesses to deficiencies and ways to interact with a gas system that has been converted across to hydrogen and then use the storage or line pack that's so important in the difference between a molecule and an electron. We're also doing work when you're designing future systems associated with that relative economics of pipelines versus power lines to say, if you were to develop a new system, at what point and where would you optimise putting electrolyzers so that you actually use pipelines as well for both the economics and the storage. And Steve already mentioned the fact that the pipeline designs can be increased in diameter for marginal storage costs that become incredibly efficient compared to some of the other ways of storing large-scale energy. I also highlight some of the early work we've done on the feasibility of Australia to use different means of underground gas storage, as is used today, to store energy during summer, to have the capacity for the system during the winter in geological storage. Now, that can be by a number of means. That can be, as is already done around the world, salt caverns, but it can also be depleted oil and gas reservoirs, aquifers, and even engineered caverns. And the scale and the capacity to actually use that in a future molecule system is quite incredible and will be an important part of balancing. And then I also mentioned, particularly with Robin Battingham in the room, that we've been part of the Net Zero Australia initiative, which is a formidable piece of modelling work released last week, looking at the complete integration of a net zero system for Australia, including, most importantly, export. In the steels area, where I mentioned that we had a working group, this is a critical area of endeavour, where the issue of hydrogen embrittlement, or the embrittlement potential as hydrogen is put into steel systems, is crucially important to have a much deeper understanding. And we're working on all elements of this, particularly fracture mechanics elements of it that are already a key part of pipeline design, which Australia is so formidable in. But a deeper understanding of that is crucial to understand how and where and at what pressures we can put hydrogen into existing piping systems. It's important to note that under current codes, when we design a hydrogen pipeline system, it will actually largely be the same steel. Could be slightly different differences in it, but key is understanding the conditions upon and particularly pressures that can operate there, and incorporating that into standards that are going to have to change to incorporate hydrogen into piping design. And we're actually working on a first step in that journey, which we're calling a code of practice, as part of the journey to that being standardized or codified in that area. We're also doing testing work on one specific pipeline north of Perth for APA, looking at testing under hydrogen conditions associated with standards that are there, to look at the potential for that pipeline specifically to be converted to hydrogen. So I bring up this picture here, which is a tensile testing machine that we're commissioning as we speak in the University of Wollongong, and it's one of 3 that we've got ordered that allows the ability to do testing of steel samples, small steel samples for fracture, for fatigue testing, and for tensile testing in a hydrogen atmosphere. Now, there's only a few places in the world that are currently doing this, and this will actually allow Australia to explore pathways under the current pipeline code that does incorporate hydrogen for increased capability of those pipelines once you understand the conditions of the pipe itself. I'll now move on to plastics, where there's a lot of work going on overseas, but equally here, we have a couple of projects that are looking at the long-term testing of plastic pipes under hydrogen conditions. It's one thing to deeply understand how the upgraded pipes that Robert's already mentioned operate in terms of leaks or tightness of the system, but another element is to actually understand over long duration testing, are there any changes that are there, both in standard areas and also areas, for instance, of stress concentrations. Same with the fittings and joints. So this sandpit, which is located down at the Deacon's High Cell facility down at Warren Ponds, is quite a large facility encompassing almost every set of distribution piping we have in Australia. And another area that I'd touch on, given that we're trying to look at all across the value chain at the moment and anticipate things that we have to have new knowledge on, is that of elastomers, the plastic components that might be sealing, for instance, in meters, which Robert also already mentioned. And we've actually tested a very large range of the elastomers and are aware of those that show no propensity for change and those that we need a deeper understanding where there is some indications under hydrogen. I'm just going to move to our international linkages. We're being connected to a number of very similar applied pipeline research groups for a long time now as a community, particularly the Pipeline Research Council International of North America and the European Pipeline Research Group that are showed there. But with the breadth of activities in hydrogen and considering hydrogen being inserted into the pipeline system, many other groups as well, and including the Institute of Gas Engineers and Managers in the UK, and the Gas Energy Research Group. And these are now manifesting themselves in quite regular interactions between groups that are all working on many of the same questions and making sure that we're leveraging off each other's experiences. We're not unnecessarily duplicating work and we're sharing and collaborating wherever possible. From that, we get a deeper understanding of what's going on in Europe. And I already mentioned the European Hydrogen Backbone Project, which I've shown a link there at the bottom, but also the scale at which this is developed to link right across Europe. And having just got back in June from visiting particularly the UK, what's very evident out of the issues going on in Europe at the moment is an acceleration of the hydrogen transition. And I've mentioned 2 components to it here. The previous target under the European Commission's policy of Fit for 55 was about 5 million tonnes of hydrogen, which is a very large amount, being commissioned and running by 2030. But under the more recent Repower EU targets, that's jumped to 20 million tonnes, and half of that by domestic production in Europe and half by import a story very important for Australia, particularly on the import-export story. But with that, the need for governments around Europe to actually accelerate what were targets for pipeline conversion in 2030 or 2040 to earlier dates. So you can see a lot of pressure, a lot of tension here. And with it, programs occurring in countries like Netherlands, Germany already on this, and I'll just pick out one or two from the UK now to close on for a deeper understanding. I do mention at the bottom there too, it's not just hydrogen here. As part of Europe separating from dependency, particularly on Russia, the biomethane story, which I mentioned at the beginning, has jumped in 2030 from a current approximately 3 BCMs, billion cubic metres of biomethane, to 35 being targeted in 2030. So you can see tenfold type increases there that the Europeans are targeting. Okay, I said I'd mention a little bit from the UK in just my last couple of minutes. The UK has a backbone in a similar way that links the sort of 6 main industrial hubs. It's actually called Project Union, and associated that they have a project called Future Grid, which is simulating and testing up at in Northern England a circuit of existing high pressure mains under hydrogen conditions. And that is being done adjacent with what's called the H21 facility that does similar simulation for the distribution network, and also a hydrogen house called High Street. And this simulates the whole British gas system under real world conditions. This is part of what I would call their evidence gathering for decisions they're making on the role of hydrogen and clean gases in their system, through both the transmission system and distribution, and all the way through to residential. That's expected to lead to their decisions in 2025, 2026. This Future Grid project that I just mentioned, being at the high pressure end, will be running over a longer period of time. First of all, testing at 2% hydrogen, then 20%, and then 100% through all of those assets. And then collecting all of that information and using that as part of their safety risk analysis through their QRA. So that's one very large investment by the UK, both government and gas industry. And it's part of a number that are occurring over there that we stay very close to, not duplicating this, but complementing it. In the gas distribution area, they've already had what they call high deploy, which was testing at the higher levels of blends. 20% test actually at a university, which occurred successfully 18 months or so ago, and then more recently 20% to about 600 homes. We haven't done 20% in Australia yet. We have blending at 2% levels in Sydney and 5%, as Robert mentioned, in Adelaide. But the UK system is now successfully tested up to 20%. Now, 20% by volume doesn't achieve major steps in terms of decarbonisation. We have to be honest about that. It is part of the stepping stone, the gradual stepping stone through to the 100%. And for that, I mentioned the H21 project, just to give you an idea of these different high type projects over in the UK, which is doing the analysis and testing of their gas distribution up to 100%. And also the High for Heat program, which instead of the gas distribution is looking inside the homes at the safety of operating the 100% hydrogen facilities inside residential, with the criteria being as safe as or better than the current natural gas system. And that leads into one of a couple of the 100% demonstration projects that the British are involved in at the moment, one that I drove to in June, and that is the Fife H100 project in Scotland, where a duplicate 100% green hydrogen system will be installed in the region of Fife, north of Edinburgh, and 300 to 400 homes will be opting in for running on hydrogen. That's a pretty exciting project from the point of view of clean gases being deployed. The appliances have already been developed for that, and many of you would have seen hot water heaters and combi heaters and others that are deemed to be hydrogen ready, meaning they're designed for hydrogen, but can also run on natural gas with a very easy switchover in the future between the two gases, which is to deal with one element and minimise one element of a potential future transition in that area. And following on from the Fife project that's expected to start next year, is the final part of this evidence gathering for the UK, and that is what's called the Hydrogen Village program, where there's 1 or 2 villages that are already being nominated for around 500 to maybe 2,000 people, where instead of laying new pipes, it'll run through the existing system to those homes. So I'm going to finish there. Hopefully we've done the overview of the system well, and it's a big system, big complex one, where we've tried to put enough perspective there and then give some insights of both about work that is occurring here in Australia and also a bit of an overseas perspective, with a little bit of the very large amount of research work that is progressively going on in Australia. I look forward to a world, and I think we're heading there, and I particularly see it in the university system at the moment, where the future of clean electricity and clean gas is working together on all of these and leveraging off the relative merits of both, understanding particularly the issue of where there's advantage in one system over another. There is no doubt we're in a world of massive move to electrification, but there's also many parts, such as in heavy industry, heavy duty transport and those other areas, and particularly storage and the heating system potentially, as I've explained here, that the UK is at the leading part of final decisions in that area that we actually look forward to. So with that, I always thank all of the participants and partners in the CRC